Hello, this is video 5 on the Sn1 reaction. We saw in the Sn2 video that this material here is unreactive to Sn2 because of steric hindrance of these large groups at this tertiary carbon, a carbon with 3 carbons attached. Interestingly, if you mix these materials together, you can get this product. So how does that happen? It happens via the Sn1 mechanism, where one molecule actually dissociates. That's why we call this a unimolecular reaction, because the rate limiting step is the dissociation of just one molecule. It doesn't depend on 2 molecules colliding like in Sn2. When these 2 electrons comprising that bond depart with the bromine, we get a tertiary carbocation here. The OH minus can come and form a bond directly to that, giving us our product that we see above. And for completeness, you could say that you have Br minus forming over there. So Sn1 reactions occur primarily when a tertiary carbocation can form, but they can also occur through a secondary carbocation. So here we have a secondary carbocation, a carbon here bearing the leaving group right there. That carbon has 2 carbon groups attached to it and a hydrogen, so that's a secondary carbon. When this bond breaks, dissociation, we have the secondary carbocation forming. The OH minus can come and bond directly, forming that bond. But Sn1 can't occur via a primary carbocation because primary carbocations basically cannot exist. So this is no reaction. You cannot have this dissociate and form this primary carbocation. So we have the designations primary, secondary, tertiary to abbreviate those words. Therefore, the order of carbocation stability is tertiary, most stable, carbocation, primary, impossibly unstable, and this middle ground of the secondary. So we can conclude that if you have a tertiary carbon with a leaving group on it that would form a tertiary carbocation, that reaction will only go Sn1. It cannot go Sn2. If it's a primary carbon, it can only go Sn2, cannot go Sn1. If it's a secondary carbon, it can go either or both of these mechanisms. There's reaction conditions that would favor one versus the other. And mainly you can read about that in detail in the book. I may mention it from time to time. Let's look at another example. We talked about transition states in Sn2 reactions. Here's our example. This dissociation would result in a hypothetical transition state. Remember, this is an analysis where we see bonds in the process of forming and breaking. So this is not a hash mark saying it's going back directionally. This is a bond breaking in the process of breaking. And of course, transition states are always higher in energy. So pretty simple transition state for the Sn1 mechanism, just that dissociating bond. You get the tertiary carbocation, you get your nucleophile coming in, still called a nucleophile, forming that bond. Stereochemistry is important in these reactions, just like in Sn2 reactions. So carbocations, if we examine them more closely, are planar. You see how that is in the plane. All of these bonds are in the plane. Actually, there's an empty p orbital. So carbocations are actually sp2 hybridized with an empty p orbital. And so the nucleophile can come in and bond to either face, top face or bottom face of the molecule as we call it, with equal likelihood. If this carbon that the reaction is taking place on is chiral, then you'll get a 1-to-1 mixture of R and S configurations. Here's an example of that. This is a chiral center right here. Chiral carbon. It's actually in the S configuration. Again, review these if you need to. That goes back to first quarter. Here's our tertiary carbocation, planar. Let's say we introduce this carbon nucleophile. It can bond with equal likelihood, since this is flat, top or bottom face, either or, not both. Well, both, not both at the same time, obviously. This will lead to a 1-to-1 mixture, equal amounts, of the S and R enantiomers, right? These are enantiomers. And so one of the enantiomers we would refer to as retention of configuration compared to the starting material is what we're talking about. While the other equal amount is inversion of configuration, similar to what you would get, well, with SN2 if it could go SN2. A few other important considerations, actually for both SN1 and 2, but we'll focus on SN1 still here. Water is a more realistic nucleophile. If you think about the formation of a carbocation, it's a plus charge. Plus charges are favored in acidic solutions. The formation of plus charges. Solutions. So it's really unlikely that an OH minus nucleophile is going to be hanging around waiting for that plus charge to form and then going and bonding directly like I showed above. So water is much more likely. In fact, water in aqueous acid is the most likely. So when water is used, there's one more simple step involved. And so if you track through this, here we have a tertiary carbon with a leaving group. The bromine dissociates. You get your tertiary carbocation. Now here comes water bonding directly, just like an OH minus would, because it's got these lone pair electrons that are nucleophilic, Lewis bases, right? Electron pair donor. Now reassessing formal charge, once this bond is formed, this has a plus charge. Those formal charges are so critical for knowing what's going on. This can complete with another water molecule coming in and just removing or deprotonating this proton. This is bond forming. Bond breaking in the direction of a plus charge makes a lot of sense. Make sure your arrows start and end where they're exactly supposed to. You want to communicate that. That results in your alcohol product, and this is not chiral, so you're not really going to have to go and show the R and S mixtures. And notice acid is regenerated, so it's probably an acid catalyzed reaction. Here's another quick little video showing that. All right, so there's the water coming in and then the proton being removed. I'll let this go through. What you see on the left is what we're seeing on the right. OH2 comes in, OH2 removes the proton. There's your alcohol. And it's just showing you the S configuration, but it could result in the R configuration too if it comes in from the top face instead. Let's look through it one more time. And then we're out of time. So here's McMurray reading, and then another short video coming up on energy considerations.